Please all rise. Let us pray first. Okay, Mr. Alejandro, please come forward and lead the prayer. Amen. Good morning, class. Before you take your seat, please pick up some pieces of paper under your chair and arrange your chair properly. So, secretary, who is absent for today? Okay, none? Continue your perfect attendance. So before we will proceed to our next topic, let's have a recap first. So, what is our topic last meeting? Okay, Mr. Abdullah. Okay, very good. Our topic last meeting is all about Wilson's theorem. It seems that you still remember our topic last meeting, and it seems that you already understand it. So let's move to our next topic. So our topic for today is all about Euler's phi function or Euler's tangent function. So the objective of this lesson is at the end of the lesson, the students will be able to know the proponent of the Euler's phi function and define the meaning of Euler's phi function. Next is to identify the theorems of Euler's function and prove the given theorems and appreciate the importance of Euler's phi function. But before we proceed to our discussion, let's have an activity first. So this column will be the group 1, then group 2, and group 3. So our activity is all about find me. Arrange first the jumbled letters, which serves as a clue in order to find the words in this box. So, I'll give you 5 minutes to answer this activity. So, the timer starts now. Class, be quiet. Are you done? Okay. Last 1 minute. Okay, time's up. Okay, exchange your paper to other group. Group 1, your paper should be in the group 2, and group 2, your paper should be in group 3, and group 3, your paper should be in group 2. So now let's check your activity. So number 1, it is function. So in the box, this would be the function. So number 2, it is theorem. So the theorem will be in here, going up. Next is number 3, phi function. So the phi function is located in this area. Going down. Next is totative, which is in this area. And last is the integer, which is in this area. Okay, are you done checking? Okay, raise your paper. Who got perfect? Okay, very good. It seems that all of you got correct answer. Okay, give yourself a round of applause. Okay, now let's proceed to our discussion. Okay, lend your ears. So, proponent of Euler's phi function. Leonhard Euler was born on April 15, 1707 in Basel, Switzerland. He died on September 18, 1783 in St. Petersburg, Russia. He is Swiss mathematician and physicist, and he is one of the founders of pure mathematics. He has not only made decisive and formative contribution to the subject of geometry, calculus, mechanics, and number theory, but also developed methods for solving problems in observational astronomy and demonstrated useful application of mathematics in technology and public affairs. Leonhard Euler introduced the function in 1763. However, he did not at the time choose any specific symbol to denote it. In a 1784 publication, Euler studied the function further, choosing the Greek letter pi to denote it. He wrote pi d for the multitude of number less than d and which have no common divisor with it. Next, this definition varies from the current definition for the tangent function at d is equal to 1, but is otherwise the same. The now standard notation phi of a comes from Gauss 1801 Treatise Disquisitiones Arithmeticae, although Gauss didn't use parentheses around the argument and wrote phi of a, thus it is often called Euler's phi function or simply the phi function. In 1879, J.J. Sylvester coined the term tangent for this function, so it is also referred to as Euler's tangent function, the Euler's tangent, or Euler's tangent. Jordan's tangent is a generalization of Euler's. The cotangent of n is defined as n minus phi of n. It counts the number of positive integers less than or equal to n that have at least one prime factor in common with n. In number theory, Euler's tangent function counts the positive integers up to a given integer n that are relatively prime to n. It is written using the Greek letter phi as phi of n or phi of n, and may also be called Euler's phi function. In other words, it is the number of integers k in the range 1 less than or equal to k is less than or equal to n, for which the greatest common divisor, which is the GCD of n and k, is equal to 1. The integers k of this form are sometimes referred to as dotatives of n. So Euler's function phi of n for all positive integers, n is defined as phi of n is equal to 1. For n is equal to 1 and for n greater than 1, phi of n is equal to number of integers less than n and co-prime to n. So note, co-prime or relatively prime numbers are those numbers that have only one common factor, namely 1. That means a pair of numbers are said to be co-prime when they have their greatest common factor as 1. So it will be called as co-prime if the GCD of the two numbers will be is equal to 1. So for example, find phi of 5. So here is the solution. So n is equal to 5. So number less than 5 are the 1, 2, 3, and 4. As you see, the GCD or the greatest common divisor of 1 and 5 is equal to 1. So the GCD of 2 and 5 is equal to 1. And the GCD of 3 and 5 is equal to 1. And the GCD of 4 and 5 is equal to 1. Is it co-prime? So the GCD of 1 of 5 is equal to 1, which means it is co-prime when the GCD of the two numbers will be equal to 1. So therefore, it is yes, it is co-prime. The GCD of 2, 5 is equal to 1. Yes, it is also co-prime. The GCD of 3 and 5 is equal to 1. Therefore, it is also co-prime. And the GCD of 4 and 5 is equal to 1. It is also a co-prime. So, if you count it in the phi of 5, it has 4 co-prime. Therefore, phi of 5 is equal to 4 because in phi of 5, there are 4 co-prime. So that phi of 5 is equal to 4. So, there is any questions or clarification? Okay, if none, let's proceed to another example. So, find phi of 8, where n is equal to 8. So, number less than 8 are 1, 2, 3, 4, 5, 6, and 7. So, as you see, the GCD of 1 and 8 is equal to 1. The GCD of 2 and 8 is equal to 2. And the GCD of 3 and 8 is equal to 1. And the GCD of 4 and 8 is equal to 4. And the GCD of 5 and 8 is equal to 1. And the GCD of 6 and 8 is equal to 2. And the GCD of 7 and 8 is equal to 1. So let's find those numbers who are co-prime. So the GCD of 1 and 8 is equal to 1. Therefore, it is co-prime. The GCD of 2 and 8 is equal to, therefore, it is not co-prime because the GCD is not equal to 1. So, the GCD of 3 and 8 is equal to 1. It is co-prime. And the GCD of 4 and 8 is equal to 4. Therefore, it is not co-prime. Next, the GCD of 5 and 8 is equal to 1. Therefore, it is co-prime. And the GCD of 6 and 8 is equal to 2. Therefore, it is not co-prime. Next, the GCD of 7 and 8 is equal to 1. Therefore, it is co-prime. So, let's count the co-prime. So, 1, 2, 3, and 4. Therefore, the phi of 8 is equal to 4 because in this phi of 8, only 4 of these numbers are co-prime. Is there any question before we proceed to another? Okay, if it's not, so let's proceed. Notice that phi of 1 is equal to 1 because the GCD of 1 is equal to 1 in the event n greater than 1, then the GCD of n in n is equal to n not equal to 1. So that phi of n can be characterized as the number of integers less than and n relatively prime to it. The function phi is usually called the phi function. Sometimes the indicator or tangent after its originator. The functional notation phi of n, however, is credited to Gauss. If n is a prime number, then every integer less than n is relatively prime to it. Whence, phi of n is equal to n minus 1. On the other hand, if n greater than 1 is composite, then n has a divisor d such that 1 is less than d and d is less than n. It follows that there are at least 2 integers among 1, 2, and 3 until n that are not relatively prime to n, namely d and n itself. So as a result, phi of n less than or equal to n minus 2, this proves that 4n is greater than 1. Phi of n is equal to n minus 1 if and only if n is prime. The first item on the agenda is to derive a formula that will allow us to calculate the value of phi of n directly from the prime power factorization of n. So, this would be the theorem 1. If p is a prime and k is greater than 0, then phi of p raised to the power of k is equal to p raised to the power of k minus p raised to the power of k minus 1 is equal to p raised to the power of k times 1 minus 1 over p. So, let's move to the proof. Clearly, the GCD of n and p raised to the power of k is equal to 1 if and only if p does not divide n. There are p raised to the power of k minus 1 integers between 1 and p raised to the power of k divisible by p, namely. So, p, 2p, 3p until p raised to the power of k minus 1 times p. Thus, the set 1, 2 until p raised to the power of k contains exactly p raised to the power of k minus p raised to the power of k minus 1 integers that are relatively prime to p raised to the power of k, and so by the definition of the phi function, phi of p raised to the power of k is equal to p raised to the power of k minus p raised of the power of k minus 1. So let's move to the example. For an example, we have phi of 9 is equal to phi of 3 squared is equal to 3 squared minus 3 is equal to 9 minus 3 is equal to 6. It is the factorization of 9, which is, if we multiply 3 by itself, it is equal to 9. So, as we go back to the formula, it is p raised to the power of k minus p raised to the power of k minus 1. So, the p raised to the power of k, it is equal to 3 squared. So, then minus 2p raised to the power of k minus 1, which is 3 squared. So, minus 1 is equal to 3. So, 3 times 3 is equal to 9. Then, minus 3 is equal to 6. The 6 integers less than and relatively prime to 9 being 1, 2, 4, 5, 7, 8. To give a second illustration, there are 8 integers that are less than 16 and relatively prime to it. They are 1, 3, 5, 7, 9, 11, 13, 15. Theorem 1 yields the same count. So, for example, phi of 16 is equal to phi of 2 raised to the power of 4, which is the factorization of 16, which is 2 times 2 times 2 times 2 is equal to 16. So, as we go back to the formula, which is p raised to the power of k minus p raised to the power of k minus 1. So, the p raised to the power of k, which is the 2 raised to the power of 4, then minus p raised to the power of k minus 1, which is 2 raised to the power of 4 minus 1. So, it becomes 2 raised to the power of 3. So, 2 times 2 times 2 times 2 is equal to 16. So, 2 times 2 times 2 is equal to 8. So, 16 minus 8 is equal to 8. So, is there's any question? Okay, if none, let's proceed to other examples. So, theorem 1. So, phi of 575. So, solution. So, phi of p raised to the power of k is equal to p raised to the power of k minus p raised to the power of k minus 1. So, n is equal to 575, which is, this would be our n, is equal to 5 squared times 23, which is the factorization of 575. So, next, phi of 575 is equal to, which is the 5 squared, which is the p raised to the power of k minus p raised to the power of k minus 1, which is 5 squared minus 1 is equal to 5, and times 23 minus 23 raised to the power of 0, which is 23 minus 1 is equal to 0. Therefore, 5 times 5 is equal to 25 minus 5 is equal to 20. Then 23 minus 1, because when a number raised to the power of 0 is equal to 1, so 23 minus 1 is equal to 22. So 20 times 22 is equal to 404. So, do you have any question? Okay, none. Let's proceed to another example. So, phi of 484. So, the solution, which is phi of phi raised to the power of k, is equal to p raised to the power of k minus p raised to the power of k minus 1. So, our n is equal to 484, and the factorization is 2 times 2 times 11 times 11 is equal to 484, and it is also equal to 2 squared times 11 squared. So we will use this. So phi of 484 is equal to 2 raised to the power of 2 minus 2 times 11 raised to the power of 2 minus 11. Same process, which is p raised to the power of k is 2 squared. So minus 1, it is equal to 2, and also 11 raised to the power of 2 minus 1 is equal to 11. Therefore, 2 times 2 is equal to 4, minus 2 is equal to 2. Then 11 times 11 is equal to 121 minus 11 is equal to 110. So 2 times 110 is equal to 220. Now, is there any question or clarification before we proceed to the theorem 2? Okay, it's none. So let's proceed to the next topic, which is the lemma. We now know how to evaluate the phi function for prime powers, and our aim is to obtain a formula for phi of n based on the factorization of n as a product of primes. The missing link in the chain is obvious. Show that phi is a multiplicative function. We pave the way with an easy lemma. Lemmas are given integers a, b, c. GCD of a and bc is equal to 1 if and only if GCD of a and b is equal to 1, and the GCD of a and c is equal to 1. Proof. First, suppose that the GCD of A and BC is equal 1, and put D is equal to GCD of A and B. Then D divides A and D divides B. Whence D divides A and D divides B. This implies that GCD of A and BC is greater than or equal to D, which forces D is equal to 1. Similar reasoning gives rise to the statement GCD of A and C is equal to 1. For the other direction, take GCD of A and B is equal to 1. 1 is equal to the GCD of A and C, and assume that GCD of A and BC is equal to D sub 1 greater than to 1. Then, D sub 1 must have a prime divisor P, because D sub 1 divides BC. It follows that P divides BC. In consequence, P divides B or P divides C. If P divides B, Then, by virtue of the fact that P divides A, we have GCD of A and B greater than or equal, no? Greater than or equal to P, a contradiction. In the same way, the condition P divides C leads to the equally false conclusion that GCD of AC is greater than or equal to P. Thus, D sub 1 is equal to 1 and the lemma is proven. So, let's proceed to the theorem 2. If the integer n is greater than 1, as the prime factorization n is equal to P sub 1 raised to the power of K sub 1, P sub 2 raised to the power of K sub 2, until P sub r raised to the power of K sub r, then phi of n is equal to P sub 1 raised to the power of K sub 1 minus P sub 1 raised to the power of K sub 1 minus 1 times P sub 2 raised to the power of K sub 2 minus P sub 2 raised to the power of K sub 2 minus 1 until P sub r raised to the power of K sub r minus P sub r raised to the power of K sub r minus 1. So, is equal to 1 minus 1 over P sub 1 times 1 minus 1 over P sub 2 until 1 minus 1 over P sub 3. So, for example, let us calculate the value of phi of 360. For instance, the prime power decomposition of 360 is 2 raised to the power of 3, 3 raised to the power of 2 times 5, and theorem 2 tells us that phi of 360 is equal to 360 times 1 minus 1 half times 1 minus 1 third times 1 minus 1 fifth is equal to 360 times 1 half times 2 third times 4 fifth is equal to 96. So, let's proceed to the example number 2. So, phi of 484. Phi of n is equal to n times 1 minus 1 over P sub 1 times 1 minus 1 over P sub 2 and so on. N is equal to 484. And is equal to 2 times 2 times 2 times 11 times 11 is equal to 2 raised to the power of 2 times 11 raised to the power of 2. So, phi of 484 is equal to 484 times 1 minus 1 half times 1 minus 1 over 11 is equal to 484 times 1 half times 10 over 11 is equal to 484 times 5 over 11 and is equal to 220. So, is there any question or clarifications? Just raise your hand if you have any question according to our lessons. Okay? If not, let's proceed to our group activity. Okay, group yourself into 3. Then, this would be the group 1, group 2, and group 3. Okay? Just go to your group quietly. So, I'll give you 10 minutes for this activity, and after that, choose one representative to present your output in front. So the time starts now. Okay, 5 minutes left. Okay, time's is up. Present now your output. And let's check your output also. So, I'll give 100 points to those who got perfect this activity. So, let's check. Okay, number 1, phi of 650. So, Rn is equal to 650 is equal to 2 times 5 raised to the power of 2 times 13. So, phi of 650 is equal to 2 minus 2 raised to the power of 0 times 5 squared minus 5 times 13 minus 13 raised to the power of 0 is equal to, so 2 minus 1 is equal to 1, and 5 squared, which is 25 minus 5 is equal to 20, and 13 minus 1 is equal to 12. So 1 times 20 times 12 is equal to 240. So next, number 2, phi of 234. So n is equal to 234. So is equal to 2 times 3 squared times 13. So phi of 234 is equal to 2 minus 2 raised to the power of 0 times 3 squared minus 3 times 13 minus 13 raised to the power of 0. So 2 minus 1 is equal to 1, and 3 times 3 is equal to 9 minus 3 is equal to 6. 13 minus 1 is equal to 12. So 1 times 6 times 12 is equal to 72. So let's check number 3. Phi of 459. So our n is equal to 459. So it is equal to 3 raised to the power of 3 times 17. So phi of 459, so is equal to 3 cubed minus 3 squared times 17 minus 17 raised to the power of 0. So 3 times 3 times 3 minus 6 is equal to 18. Then 17 minus 1 is equal to 16. So 18 times 16 is equal to 288. So let's check who got perfect score. So based on your output, group 1 and group 3 got perfect scores. So therefore, they will receive a 100 points from this activity, and group 2 will receive 80 points. So get 1/4 sheet of paper and answer your quiz. Just write the letter of your answer. I'll give you 10 minutes for this question. The timer starts now. Okay, time is up. Exchange your paper clockwise. 1, 2, 3, 4, 5. So, check. The answer number 1 is A. The answer number 2 is letter C. The answer of the number 3 is letter B. So, who got perfect? Okay, very good. Clap your hands. So now, let's proceed to your assignment. Copy your assignment now. And we will check it in our next meeting. Are you done? Okay, that's all for today. Okay, thank you for participating and listening to our discussion. Goodbye, class.